In this section, we are going to learn about increasing and decreasing functions. I will give you few examples to know where do we use increasing and decreasing functions concept. For instance, the speed of an object, we might want to know when the speed is increasing or decreasing. That is, when the object is accelerating or decelerating. Next example, if F is the population of the city, we might be interested in knowing when the population is increasing and when it is decreasing. That is, when the population is growing or declining. Another example, in business, increasing and decreasing function means the difference between making money and losing money. And another important application of increasing and decreasing function is in curve sketching. Now let us see what is an increasing function. A function is said to be an increasing function when y value increases as x value increases. Let us consider these graphs. In this interval, in the first figure, we say that the function is increasing. And in the second figure also, in the given interval, the function is increasing. Now in the third figure, in this given interval, we say that the function is strictly increasing, and in the fourth figure, again in this given interval, the function is strictly increasing. Now for a given function y is equal to f of x, when x1 is less than x2 and f of x1 is less than or equal to f of x2, like in the first two figures, we say that the function is increasing in that given interval. And when x1 is less than x2 and f of x1 is strictly less than f of x2, as in the third and the fourth figures, we say that the function is strictly increasing. Notice the sign which we use here. In the first two figures, in this interval, the function is a constant function. F of x values are same for all values of x in this interval. Similarly, in the second figure also, in this interval, f of x values are the same. So when we talk about the whole interval, f of x1 is less than or equal to f of x2 in the first two figures. Therefore, we say that the function is increasing. Whereas in the third and the fourth figures, in the given interval, for x1 less than x2, we have f of x1 strictly less than f of x2. In these two figures, no two values of x will have the same f of x values. Therefore, we say that the function is strictly increasing in the given interval. The derivative of a function may also be used to determine whether the function is increasing or decreasing on any interval in its domain. See the first figure. In this interval, the line segment makes an acute angle with the positive direction of x-axis. Therefore, tan theta is positive. Therefore, the slope of this line segment m is greater than 0. In the next interval, it is a constant function. Therefore, the slope m is equal to 0. And in the third interval, again the line segment, when it is produced, it makes an acute angle with the positive direction of x-axis. Therefore, slope is greater than 0. M is greater than 0. Now see the second figure. In this interval, if we draw a tangent at any point of this curve, when produced, it makes an acute angle with the positive direction of x-axis. Therefore, in this part of the graph, slope is greater than 0. Now in the next interval, it becomes a constant function. Therefore, slope is equal to 0. Now in the third interval, if we draw a tangent at any point of this part of the graph, this tangent also when produced, it makes an acute angle with the positive direction of x-axis. Therefore, slope in the third interval, m is greater than 0. Now in the first two figures, in the whole of the given intervals, we can say that m is greater than or equal to 0, and this is the condition for an increasing function. In the first two figures, we can say that the function is increasing. we cannot say that it is strictly increasing. Now in the third figure, in this given interval, the line when produced, it makes an acute angle with the positive direction of x-axis. Therefore, slope of this line segment is greater than 0 as tan theta is going to be positive. And in the fourth figure, again in this given interval, if we draw a tangent at any point of this graph, it makes an acute angle with the positive direction of x-axis. Therefore, the slope is greater than 0. From the third and the fourth figures, we can say that the condition for strictly increasing function is m is strictly greater than 0. In all the four figures, we can say that the function is increasing. So remember, it is okay to say that it is increasing, but it is not okay to say that it is strictly increasing unless m is strictly greater than 0. Now let us see what is a decreasing function. A function is decreasing when y value decreases as the x value increases. See these four graphs. In the first two graphs, the functions are decreasing. In the third and the fourth graphs, the functions are strictly decreasing. For y is equal to f of x, when x1 is less than x2 and f of x1 is greater than or equal to f of x2, we say that the function is a decreasing function. Whereas, when x1 is less than x2 and f of x1 is strictly greater than f of x2, we say that the function is strictly decreasing. Notice the sign here. It should be strictly greater than sign. Now let us see the conditions for decreasing and strictly decreasing functions in terms of their slopes. In the first figure, in this interval, the slope of the curve m is less than 0 as this line segment makes an obtuse angle with the positive direction of x-axis. And in the next interval, it is a constant function, so slope becomes 0. And in the third interval, the line segment makes an obtuse angle with the positive direction of x-axis. Therefore, in this interval also slope is less than 0. So, throughout the given interval, m is less than or equal to 0. Similarly, in the second figure, we will take intervals. In the first interval, if we draw a tangent at any point of this curve, the tangent makes an obtuse angle with the positive direction of x-axis. Therefore, the slope m is less than 0. And in the second interval, it becomes a constant function. Therefore, the slope is equal to 0. And in the third interval, if we draw a tangent at any point in this interval, this also makes an obtuse angle with the positive direction of x-axis. Therefore, slope of the curve in this interval is also less than 0. See the first two figures. We can say that for a decreasing function, m should be less than or equal to 0. Now see the third figure. In the given interval, the slope of this line segment is strictly less than 0. Never it becomes equal to 0 in between. Therefore, we say that the function is strictly decreasing. Similarly, in the last figure, if we draw a tangent at any point of this curve in the given interval, the tangent line makes an obtuse angle with the positive direction of x-axis. Therefore, slope of the curve in the given interval is strictly less than 0. Therefore, the condition for a strictly decreasing function in terms of the slope is m is strictly less than 0. Now consider this graph y is equal to f of x. So, in the given interval a to b, we say that the function is neither increasing nor decreasing. If we take intervals, let us take this as c, d, e. In the interval a to c, the function is an increasing function, and in the interval c to d, it is a decreasing function. In the interval d to e, it is an increasing function, and in the interval e to b, it is a decreasing function. So in these sub-intervals we can say that the function is increasing or decreasing, whereas if we consider the whole interval a to b, we should conclude that it is neither increasing nor decreasing. Now let us learn about the constant functions. Constant functions are horizontal lines. Consider any horizontal line parallel to x-axis. We know that its slope is equal to 0. If we have a graph, by looking at the graph, we are able to make out which part of the graph is increasing and which part of the graph is decreasing. So without using graphs also, using derivatives, we can find the intervals in which the function is increasing or decreasing. Now let us see the first derivative test for increasing and decreasing functions. So using the derivative, we are going to check whether the function increases or decreases in that particular interval. This theorem can be proved using mean value theorem. Therefore, the conditions of mean value theorem are applied here. That is, f should be a continuous function on the closed interval a comma b and differentiable on the open interval a comma b. And f is an increasing function in the closed interval a comma b if f dash of x is greater than or equal to 0 for all x values in that interval. And f is strictly increasing in the open interval a b if f dash of x is greater than 0 for all values of x in the interval a b. The next point, f is decreasing in the closed interval a b if f dash of x is less than or equal to 0 for all values of x in that interval, and f is strictly decreasing in the open interval a b if f dash of x is less than 0 for all values of x in the interval a b. The next point, f is a constant function in closed interval a b if f dash of x equal to 0 for all values of x in the interval a b. Now let us see the steps to check whether the function is increasing or decreasing in the intervals of its domain. The first step is finding the critical values of the function f. What are critical values? C is a critical value if f dash of c is equal to 0 or f dash of c is not defined. Let us consider this graph y is equal to f of x. So the turning points of the graph are the critical points because the tangents at these points will be parallel to x-axis, so f dash will be 0. So this is one critical point C1 and this is another critical point C2 where f dash of C1 and f dash of C2 both are 0. Now see the second graph. It is a continuous function, but it is not differentiable at this value c. We know that when we have sharp turning points, the function won't be differentiable at that point. Here f dash of c is not defined. Whereas in this figure we have two critical points, f dash of c1 is 0, f dash of c2 is also 0. Therefore, the critical points are nothing but where f dash is equal to 0 or where f dash is not defined. The second step is we divide the domain of the function into sub-intervals at these critical points. Step 3. Take any point p in each interval and check the sign of f dash of p. If f dash of p is greater than 0, then f is increasing on that sub-interval, and if f dash of p is less than 0, then f is decreasing on that sub-interval. While doing questions, I will explain these points in detail. Let us do exercise 6.2. Question number 1. Show that the function given by f of x equal to 3x plus 17 is strictly increasing on R, where R is the real number set. Our first step is finding f dash of x. F dash of x is 3 into 1 plus 0, which is 3, and it is always positive. Whatever the value of x is, f dash of x is positive. Therefore, f of x is strictly increasing on R. Second question, show that the function given by f of x equal to e raised to 2x is strictly increasing on R. Let us find f dashed of x. Derivative of exponential function is the same. We have to apply chain rule. Differential of e power 2x is e power 2x times differential of 2x is 2. And this is also always greater than 0 whatever the value of x is, because we know that exponential function is always a positive function. E function doesn't even take the value 0. It is always greater than 0. Since it is strictly greater than 0, we can say that f of x is strictly increasing on R. Third question, show that the function given by f of x equal to sin x is strictly increasing in open interval 0 to pi by 2 and strictly decreasing in open interval pi by 2 to pi. Let us first find f dashed of x. Derivative of sin x is cos x, and we have to find the critical points by equating f dashed of x to 0, and we don't have not defined case for cosine function, and x takes the value 0 at pi by 2 and 3 pi by 2, but 3 pi by 2 we don't have in these two intervals, so x is pi by 2. Now the first subdivision, the given interval is open interval 0 to pi by 2. We don't have any critical value in this interval, even pi by 2 is not included in this interval. We cannot split this interval into subintervals as we don't have any critical value between 0 and pi by 2. Now we will check the sign of f dashed of x in this interval. By substituting any value from this interval, we will take pi by 4, which is cos pi by 4, 1 by root 2, and it is greater than 0. Or we can say that 0 to pi by 2 is the first quadrant. In the first quadrant, cos x is greater than 0. Pi by 2 is not included here. Therefore, f of x is strictly increasing in the open interval 0 to pi by 2. Now let us check for the second interval. The second interval is open interval pi by 2 to pi. We will check the sign of f dashed in this interval by substituting a value from this interval in f dashed. Pi by 2 to pi is a second quadrant. We will take 2 pi by 3, which is 120 degrees, cos of 2 pi by 3. We need not find the value of cos 2 pi by 3. Since 2 pi by 3 is a second quadrant angle, we know that cos of 2 pi by 3 is less than 0. Therefore, f of x is strictly decreasing in the open interval pi by 2 to pi. C subdivision. We have to prove that f of x is neither increasing nor decreasing in 0 to pi. In A subdivision, we have proved that in the open interval 0 to pi by 2, f of x is strictly increasing. And in B subdivision, we have proved that in the open interval pi by 2 to pi, f of x is strictly decreasing. So if we consider the interval 0 to pi, that is combining the two intervals, we can say that f of x is neither increasing nor decreasing. Question 4. Find the intervals in which the function f given by f of x equal to 2x square minus 3x is strictly increasing and strictly decreasing. Finding f dashed of x, let us differentiate 4 times x minus 3. And to find the critical values, we have to equate f dash of x to 0. We get x as 3 by 4. This is the critical point. And f dash of x is a polynomial 4x minus 3 and it is defined for all values of x. So we don't have not defined case of f dashed here. Here the domain of the function is all real values. So we will take minus infinity to plus infinity and we got one critical value 3 by 4. Now our second step is writing the subintervals. So the intervals are minus infinity to 3 by 4 and 3 by 4 to infinity. Now we will check whether f dashed is positive or negative in these intervals. We will write intervals in the first column. We will check sign of f dashed and we will decide the nature of f. The intervals are minus infinity to 3 by 4 and 3 by 4 to infinity. We will select a value from this interval and check the sign of f dashed. We will take 0. Let us substitute in f dash for checking. F dashed is 4x minus 3. 4 times 0, 0 minus 3, which is negative. Therefore, f strictly decreases in this interval. Let us check for the second interval. F dashed of, we will take the value 1 from that interval and substitute in f dash 4x minus 3. 4 times 1, 4 minus 3, which is 1 and it is greater than 0. Therefore, f strictly increases in this interval. Question 5. Find the intervals in which the function f given by f of x equal to 2x cube minus 3x square minus 36x plus 7 is strictly increasing and strictly decreasing. The first step is finding f dashed of x. It is 6x square minus 6x minus 36 plus 0. Let us simplify this by taking 6 out. Let us factorize. Product is minus 6, sum is minus 1. The numbers are minus 3 and plus 2. Therefore, the factors are x minus 3 times x plus 2. Now, after factorizing the expression of f dash, we will equate it to 0 to find the critical points. So, the critical values are x equal to minus 2 and x equal to plus 3. We won't have not defined case for f dashed. Here, the domain of this function is not mentioned. As it is a polynomial, it has to be R, which is minus infinity to plus infinity, and we have got two critical values minus 2 and 3. Minus 2 should be on the left side of 3 as it is negative. Now we will write the intervals minus infinity to minus 2, minus 2 to 3 and 3 to infinity. Now in each interval we will check whether the function is strictly increasing or strictly decreasing. Let us draw the table. In the first column we will write the intervals, and in the second column we will check the sign of f dash and we will decide the nature of f looking at the sign of f dash. The intervals are minus infinity to minus 2, minus 2 to 3, 3 to infinity. Since we have to check whether the function is strictly increasing or strictly decreasing, we won't include the critical points. We will write open intervals at the critical values. Now let us check the sign of f dash by taking a value from this first interval. We will take minus 3 and let us substitute this value in the factorization step. So it will be easy for us to decide the sign if we substitute in the factorization step. No calculation is required. 6 is positive. X minus 3, minus 3 minus 3 minus 6, which is negative, and the next bracket minus 3 plus 2 is minus 1, that is also negative. So minus into minus becomes plus. Therefore, the answer is greater than 0. So we conclude that the function is strictly increasing in this interval. Now let us check for the second interval. F dash of, we will take a value from the second interval. Let us use 0. Substitute in the factorization step. 6 is positive, 0 minus 3 is negative, 0 plus 2 is positive. Therefore, the product will become less than 0. Therefore, f strictly decreases in this interval. Now, let us check for the third interval. F dash of, we will take a value from this interval. Any value can be taken. We will take 4 and substitute in the factorization step, which is marked with red box. 6 is positive, 4 minus 3 is 1 positive, 4 plus 2 is 6, that is also positive. Product of 3 positive numbers is greater than 0. Therefore, f strictly increases in this interval. F strictly increases in minus infinity minus 2 union 3 to infinity, open intervals, and f strictly decreases in open interval minus 2, 3. This is the answer. Question number 6. Find the intervals in which the following functions are strictly increasing or decreasing. A subdivision, we will take it as f of x square plus 2x minus 5. Let us find f dash of x, 2x plus 2. We will factorize and we will equate it to 0 to find the critical values. As this is a polynomial, f dash is defined for all real values. We don't have not defined case. X plus 1 is 0. Therefore, x is minus 1, which is a critical value. As f of x is a polynomial, the domain for this function is minus infinity to plus infinity and the critical value is minus 1. Now we will write the intervals. So we will write open intervals at the critical values. Remember, for strictly increasing and decreasing questions, we should not include the critical values in the interval. We have to write open intervals at the critical values, and infinity and minus infinity are just symbols. There also we use open interval. Let us draw the table to check the sign of f dashed in these intervals. We will write the intervals in the first column, minus infinity minus 1 and minus 1 to infinity. We will check the sign of f dash and we will decide the nature of f. F dash of, let us select a value from this interval. We will take minus 2 and substitute in f dash. To check the sign, always we will use the factorization step. 2 is positive, minus 2 plus 1 is negative, therefore the product is negative. Therefore, f of x strictly decreases in this interval. Let us check in the second interval. F dash of, we will take 0. Let us substitute in f dash. 2 is positive, 0 plus 1 is also positive. Product of two positive numbers is positive, greater than 0. Therefore, f strictly increases in this interval. B subdivision, f of x is 10 minus 6x minus 2x square. We have to find the intervals in which the function is strictly increasing or decreasing. Our first step, finding f dash. 0 minus 6 minus 4x. Minus 2 is common. We get 3 plus 2x. After factorization, we will equate it to 0. 3 plus 2x is 0. Therefore, x is minus 3 over 2, which is the critical value. And f dash of x is a polynomial. It is defined for all values of x. We don't have not defined case here. Since f of x is a polynomial, the domain is R, that is minus infinity to plus infinity, and we got one critical point which is minus 3 over 2. Now let us write the subintervals. Minus infinity to minus 3 by 2 and minus 3 by 2 to infinity. We will write the open intervals because the question is asking for strictly increasing or strictly decreasing. We won't include the critical values in such cases. Let us draw the table. In the first column we will write the intervals minus infinity to minus 3 by 2 and minus 3 by 2 to infinity. We will check the sign of f dash and we will decide the nature of f. From the first interval we will take the value minus 2 because minus 3 by 2 is minus 1.5. So we will take minus 2 and we will substitute in f dash. Minus 2 is negative. 3 plus 2x. 3 minus 4. 3 minus 4 is minus 1, which is negative. Product of two negative terms is positive. Therefore, f of x strictly increases in this interval. Let us check for the second interval. We will take a value from the second interval. Let us take 0. F dash of 0 is equal to minus 2 is negative. 3 plus 0 is 3, which is positive. Product of a negative number and positive number is less than 0. Therefore, f of x strictly decreases in this interval. C subdivision, let us take the expression as f of x, which is a cubic expression, minus 2x cube minus 9x square minus 12x plus 1. We have to find the intervals in which f strictly increases or strictly decreases. Let us first find f dash of x, which is minus 6x square minus 18x and minus 12. Let us factorize. We will take minus 6 out. X square plus 3x plus 2. Product is 2, sum is 3. The numbers are 1 and 2. The factors are x plus 2 and x plus 1. Now we will equate this to 0 to find the critical values. We get two critical points. The given function is a polynomial. Therefore, the domain is the real number set R, which is minus infinity to plus infinity, and we have got two critical values, minus 2 and minus 1. Minus 2 should be written on the left side. This is a number line. Now we will write the subintervals. Minus infinity to minus 2, minus 2 to minus 1, minus 1 to infinity. Here also we have to find the intervals in which the function is strictly increasing or strictly decreasing. So we will write the open intervals at these critical points. Let us write the intervals. Minus infinity to minus 2, minus 2 to minus 1, minus 1 to infinity. We will check the sign of f dash and we will decide the nature of f. From the first interval, we will take the value minus 3 and we will substitute in the factorization step. Don't cancel that minus 6 and check the sign only in this expression. You will get a wrong answer. We see the sign and decide whether the function is increasing or decreasing. So this minus 6 changes the sign. So don't cancel that number. Minus 6 is negative. X plus 2 minus 3 plus 2 is negative. Minus 3 plus 1 is minus 2, that is also negative. Product of three negative numbers will be negative. Therefore, f strictly decreases in this interval. Now in the second interval, we will substitute minus 1.5. Minus 6 is negative. Minus 1.5 plus 2 is positive. Minus 1.5 plus 1 is negative. Product of two negative numbers will become positive. Therefore, f strictly increases in this interval. Now for the third interval, we will check with the value 0. Therefore, f dash of 0 is minus 6 is negative, 0 plus 2 is positive, 0 plus 1 is also positive. Therefore, the final answer will be negative. Therefore, f strictly decreases in this interval. Now, we will write the conclusion. F strictly decreases in open interval minus infinity to minus 2 and open interval minus 1 to infinity, and f strictly increases in the open interval minus 2 to minus 1. D subdivision. F of x is 6 minus 9x minus x square. We have to find the intervals in which the function is strictly increasing or strictly decreasing. Let us find f dash of x. 0, minus 9, minus 2x. Minus sign is common. 9 plus 2x, we will equate it to 0 to find the critical value. X is minus 9 divided by 2. The given function is a polynomial. Therefore, the domain is R, which is minus infinity to plus infinity, and we have got one critical point, which is minus 9 by 2. Now, we will write the subintervals. Minus infinity to minus 9 by 2, we will write the open intervals, because we have to check whether it strictly increases or strictly decreases. So, we should not include the critical value in these intervals. Let us write the intervals. Minus infinity to minus 9 by 2, minus 9 by 2 to infinity. We will check the sign of f dash and decide the nature of f. Minus 9 by 2 is minus 4.5. So, from the first interval, we will take minus 5 for checking. F dash of minus 5, and we will substitute in f dash minus of. So, minus times 9 plus 2x. 9 minus 10, which is minus 1 negative. Product of two negative terms is positive. Therefore, f strictly increases in this interval. Now, from the second interval, we will take 0 for checking. F dash of 0, minus sign is there outside. 9 plus 0 is positive. Product of a negative number and a positive number is less than 0. Therefore, f strictly decreases in this interval. E subdivision. F of x is x plus 1 the whole cube times x minus 3 the whole cube. This is also a polynomial. We will find f dash of x. Let us use product rule, u and v. Product rule formula is uv the whole dash is u dash v plus uv dash. U dash, chain rule has to be applied. Power has to be differentiated first and then the base. Differentiation of the base is 1 times v plus u, that is the first term, v dash 3 times x minus 3 the whole square into derivative of the base is 1. Before equating it to 0, always do factorization. 3 times x plus 1 the whole square times x minus 3 the whole square. We get x minus 3 from the first term and x plus 1 from the second term. 3 times x plus 1 the whole square, x minus 3 the whole square, 2x minus 2. We will take 2 out. 6 times x plus 1 the whole square, x minus 3 the whole square, x minus 1. So, we have done complete factorization. We will equate it to 0. We are getting 3 critical values, x equal to minus 1, x equal to 3 and x equal to 1. The given function is a polynomial. Therefore, the domain is R, the real number set, which is minus infinity to plus infinity, and we have got 3 critical values, minus 1, 1 and 3. It is a number line. Write the numbers correctly in the ascending order. Now, we will write the subintervals of the domain. Since we have to check whether it strictly increases or decreases, we will write the open intervals at the critical values. We will write the intervals minus infinity to minus 1, minus 1 to 1, 1 to 3, 3 to infinity. Sign of f dash and nature of f. From the first interval, we will take minus 2 for checking. We will check in this factorization step. F dash of minus 2. 6 is positive. Because of whole square, the next two terms are also positive. The third term, x minus 1. Minus 2 minus 1 is minus 3, which is negative. Product of these four terms will be less than 0. Therefore, f strictly decreases in this interval. Now, for the second interval, we will take 0 for checking. F dash of 0. 6 is positive. Next two terms are having whole square. They are also positive. 0 minus 1 is negative. This is also less than 0. Therefore, f strictly decreases in this interval. Now, for the third interval, we will substitute 2 and check. F dash of 2. First three terms are positive. Now, the last term 2 minus 1 is positive, which is greater than 0. Therefore, f strictly increases in this interval. Now, the last interval, we will substitute 4 and check. F dash of 4. First three terms are positive. 4 minus 1 is also positive, greater than 0. Therefore, f strictly increases in this interval. In these two consecutive intervals, the function is strictly decreasing. If you combine these two intervals, minus infinity to 1, you can say it decreases. We cannot say strictly decreases, because at minus 1, f dash is equal to 0. So, if we combine the intervals, we get the condition f dash less than or equal to 0. Therefore, we cannot use the word strictly. Similarly, these two are consecutive intervals. In these intervals, the function is strictly increasing. But if we combine the intervals as 1 to infinity, f dash is greater than or equal to 0 in this interval, because at 3, f dash becomes 0. Since f dash is greater than or equal to 0, we cannot use the word strictly here. We can only say the function is increasing. But the question is asked for strictly increasing and strictly decreasing, so don't combine these intervals. Therefore, f strictly decreases in minus infinity to minus 1 and minus 1 to 1. Open intervals, because we should not include the critical points for strictly decreasing function. Similarly, f strictly increases in 1 to 3, union 3 to infinity. Don't combine the intervals. Write them as open intervals at the critical points. Question 7. Show that y equal to log of 1 plus x minus 2x upon 2 plus x, where x greater than minus 1 is an increasing function of x throughout its domain. The domain of the function is given here. X should be greater than minus 1. That means the domain is minus 1 to infinity. Let us find the derivative dy by dx. Derivative of log of 1 plus x is 1 upon 1 plus x minus of, we will use quotient rule, u by v the whole dash is u dash v minus u v dash upon v square. U dash, derivative of 2x is 2 times 2 plus x minus 2x times derivative of 2 plus x is 1 divided by 2 plus x the whole square. 1 upon 1 plus x minus of 4 plus 2x minus 2x upon 2 plus x the whole square. We will take LCM. 1 plus x times 2 plus x the whole square. We get 2 plus x the whole square minus 4 times 1 plus x. Let us simplify the numerator. 4 plus x square plus 4x minus 4 minus 4x upon 1 plus x times 2 plus x the whole square. We get x square upon 1 plus x times 2 plus x the whole square. Now we will equate it to 0 to find the critical values. By cross multiplication we get x square equal to 0. So x equal to 0 is the critical point. Look at the denominator of dy by dx. dy by dx is not defined when the denominator becomes 0, that is at x is equal to minus 1 and at x is equal to minus 2. But these two values are not there in the domain of the function. Therefore, we have only one critical value, which is x is equal to 0. The given domain is minus 1 to infinity, and we have got one critical value, which is 0. Let us write the intervals. Minus 1 to 0 and 0 to infinity. But see the question. The question doesn't use the word strictly. In such cases, we can include the critical values. So we can take closed interval at 0. Now we can draw the table and check whether the function is increasing or decreasing in these intervals. But look at the function f dash, which is x square upon 1 plus x times 2 plus x the whole square. In these intervals, 2 plus x the whole square is positive, which is greater than 0. 1 plus x is also positive, that is also greater than 0 because the domain is x greater than minus 1. For all these values, 1 plus x is also positive. See the numerator x square, it will be greater than or equal to 0 because at x equal to 0, the numerator becomes 0. Therefore, we can say that dy by dx is greater than or equal to 0 in these two intervals. Or as I said, we can draw the table and check for each interval. In both the intervals, the function is an increasing function. We cannot use the word strictly because we have included the critical value 0. dy by dx is greater than or equal to 0 in both these intervals. And they are consecutive intervals, and in both the intervals it is an increasing function, so we will combine and write. Therefore, in the interval minus 1 to infinity, dy by dx is greater than or equal to 0. Therefore, the given function y is increasing in its domain.